Good morning, everyone. Welcome back to our e-seminar series on Translational Biomedical Engineering. It's a great pleasure for us to host Professor Amir Miri from New Jersey Institute of Technology with us today, and he will be talking about 3D bioprinted microfluidic devices for modeling biotransport and biomedical systems. But before we start, and as always, if you have any questions, feel free to use the Ask a Question box, which can be found at the bottom of your screen. Also, I'd like to mention that our next speaker will be Professor Marco Bonizato from University of Montreal. He will be talking about neurotechnologies to restore movement next week. Feel free to follow us on Twitter. Our handle is TransLBME. You can also follow me and Human on LinkedIn to get most up-to-date information about this seminar series. Last but not least, I'd like to thank Montreal Transmedtech Institute, who has been supporting us since almost the beginning of this seminar series about 2 years ago. Thank you, Montreal Transmedtech, for supporting us. With that, I'd like to invite our speaker today, Dr. Miri, who serves as the director of the Advanced Biofabrication Laboratory at the New Jersey Institute of Technology. He received his Ph.D. from McGill University, where his doctoral research involved multiscale characterization of soft tissue biomechanics using analytical tools and a variety of mechanical testing methods. Dr. Miri's postdoctoral training at Harvard MIT Health Sciences and Technology included advanced manufacturing of biomedical scaffolds and organoids using 3D bioprinting technologies. That's where I got to know Dr. Miri, and then he started working on a very cool project that was multi-material printing, bioprinting, and I think he is one of the pioneers in that field. He pioneered the design of multi-material stereolithography and then also extrusion bioprinting platforms. And that's what I was talking about. I hope he shows some slides about this technology today. It's pretty cool and colorful. I'm sure you'll enjoy it. And then he used this technology to fabricate micro tissue models and organoids. Dr. Mir's research group has worked on 3D bioprinting platforms for creating micro tissue models and microfluidic chips. He has authored more than 55 peer-reviewed articles. Some of them are in highly regarded journals such as Advanced Materials, and has presented his work at more than 20 international conferences. Dr. Mir's group has extensive experience in the development of optical bioprinters and testing the printability of cell-laden gels. So recently he has been involved in developing educational modules based on research activities, something that is a must and then a needed thing in universities and in the educational platform. So with that, I'd like to invite Dr. Miri to start his presentation, and the virtual floor is yours.
Thank you very much. Can you please confirm if you can see my screen?
We can see your screen, yes.
Okay, I'm gonna just minimize my speaker so I won't have any echo, and I'm gonna start the presentation. It's for the east of US is afternoon. Good afternoon. For some people, it might be evening. My name is Amir Miri. I'm an assistant professor of biomedical engineering at NJIT, and I'm going to present 3D bioprinted microfluidic devices for modeling biotransport in biomedical system. Since it is translational series, I have two personal statements. First of all, I thank Dr. Sawaji and Dr. Akbari for their invitation. It's an honor to present my work in this series, as many people in the field have already presented, and I have no conflict of interest to declare regarding anything related to my technology that I'm going to present and talk about today. Before I start the research slides, I'm going to talk about NJIT. For some of you who may not be familiar with the New Jersey Institute of Technology, the school is located at Newark, the city of Newark, which is very close to New York City. So we are, in terms of public transportation or using personal car, we are between 20 minutes to half an hour to Manhattan. So we are kind of considered as New York City metropolitan. And my research lab is in the third floor of Chen Building. The Chen Building is in the northern part of the campus, and our campus is shared with Rutgers University in Newark. So as you can see, the pictures were taken in January 2022. I moved from Rowan University last summer, and since summer I was establishing my lab. The lab currently is fully equipped, but at the time the pictures were taken, we were in the middle of setting up the lab. Okay, let's talk about the topic of our discussion today. So as you may be aware of the drug development and discovery, the long path that everybody has to do to go from a concept of drug design and development from the earliest stage, having the simple formulation, to the last step of reaching to the market and to the patient, there is a very, very long path. And it starts from the simple synthesis in the laboratory scale, in vitro testing, and then going to more preclinical testing, animal and human subjects. And then you apply for regulatory process that some of the presentations in the past weeks of this series were about those regulations and those steps that everybody has to follow. As you may see, there is a long-term process to go from an early synthesis that might be 3 to 5 years to reach an animal modeling, and from animal modeling to the preclinical, you may have additional between 2 to 6 years, and then you have the final regulatory that it takes at least 1 to 2 years. So when you consider the cost of a new drug, for a single drug in, for example, oncology and immunology, that is about cancers, the drug cost from synthesis to the final step, it cost $2.7 billion for the numbers in 2018. And if you consider inflation, this number might be higher at these days. And that number is not even not different for other cases like gastrointestinal or central nervous system. Still is pretty close to $1 billion. So when you look at this, even when you have a huge cost on drug development and testing, the success rate, it's pretty low. The phase 1, when you go to the phase 1 approval, is working 14%. And out of that, in phase 2, you already have 35% success rate. So you can see, even with the huge cost, the success rate to pass the regulation is pretty low and going to the preclinical human subjects. So what's the problem? The problem here is that the average cost for a single drug to reach the market in 2018 was above $985 million, close to $1 billion in terms of the material cost, the human salary, time, and other costs that you can consider as the whole package. So there is a need for us as engineers and biomedical engineering to come up with ideas that we can solve, and we can solve some of the issues and reduce some of these existing steps that can help people to reduce the amount of testing time, to minimize the cost of, for example, animal testing or human subjects by using organ-on-a-chip modeling. So people have developed organ-on-a-chip modeling in the past 2 decades. Since the idea came to academia and then the market, it has been a huge growth that people are interested to make biomimetic microenvironment to replace animal model. And those models benefit from being inexpensive compared to preclinical testing, and also have the repeatability. That's one of the things that people care when they go for drug testing. And also, when you have those organ-on-a-chip modeling, you can do drug testing and drug screening at a large scale. So that's the problem, and that's the solution statement that we are discussing today. So when you look at the history behind those preclinical and in vitro models, you can have a very simple 2D culture system that you can test the drug. That would be a simple flat petri dish. You involve the human cell lines and then you involve the drug and see their interaction. And that model can be advanced to a 3D cultures, and from the 3D cultures can be a very dynamic environment in animal model like a rodent systems that people use for testing. If you look at this pathway, we are most considering in the 3D culture, and we are trying to optimize and improve the quality of 3D cell culture system so we can have much less cost when it goes to the animal testing. And we're going to look at this process. When you talk about organ on a chip and you talk about a 3D culture system, what are the steps required to take towards that objective? When you look at this, let's see one example. Let's look at the heart. If you have a heart tissue disease that might be calcified region, and you want to look at the disease and you want to test the drug. So what we do as engineers, as a biologist, we try to take the biopsy tissue from the patient, from the human subject, and then isolate the cell line or the human cells, the primary cells. And then when you isolate the primary cell from the extracellular matrix, we put the cells in a new dynamic environment to grow and try to reach to the same level of physiological condition. And physiological condition for heart cells, it might be like a physiological function as beating or something that you may consider as the main criteria. And when you are creating that dynamic environment, you try to apply the same physical laws, the same chemical conditions that you have in vivo. And by that, you start maybe testing something like a new drug or something that you can apply. So you can see the process. It goes from patient tissue samples to a final enclosed environment that you want to use for mimicking the real in vivo tissue. So that's the idea behind organ on a chip. So organ on a chips, when you look at the components, you need, as you can see from the previous slide, you need an enclosed environment because you want to mimic the physiological condition with ECMQs, extracellular matrix. So you need an enclosed environment that also includes extracellular matrix and required factors. In addition to that, if you want to have dynamic conditioning, you need something to reach the cells, feed them, and collect the waste. So you need microfluidic channels for culture media circulation. When you are doing that as an enclosed microfluidic organ on a chip, you also need some sensing or actuation, because at most cases you need additional physical things that you want to apply on the cells, and you want to control the cell behavior over time while you have still the enclosed environment. So you need actuator, you need sensors. And if you want when you look at this, when you look at the key components, because we are engineers, we try to come up with ideas that we can improve
Dr. Miri, we lost you. Can you hear us? I think we lost Dr. Miri for a while. Can you hear us?
I think we lost his. We can see his screen.
Dr. Miri, can you hear us?
We can see.
Dr. Miri, can you hear us?
I don't think we can hear.
He can't hear us, right?
But we lost his voice.
Dr. Miri?
He's joining again. He can hear us.
Okay. He can hear us. I see in the chat, yes. So maybe you can start sharing your screen again, because we could see your screen. I mean, just one moment ago, but you kind of close it.
Right now, can you hear me?
Yes, I can hear you. So you can share your screen again. Sorry for this technical problem.
I'm gonna do that again. I restarted this page. Sorry. Where was the last time that you could hear me?
It was like in the middle of this slide that you were talking about organ on a chip. Yes, like the current challenges in organ on chips.
Okay, great. Okay,
Yeah.
I'm gonna continue. Yeah, sorry for interruption. I think it was something related to Safari setting. So I was talking about the key components, and when you look at the key components, there are challenges, and the main challenges when you do have those settings with actuators, with micro tissues, with microfluidic setup, you have the challenge of assembly, and assembly is kind of expensive in terms of labor work, in terms of materials. And also we have limited control with cell positioning in traditional systems, in conventional ones that have been into the market. And also they are very difficult to replicate the in vivo the architecture for some tissue models that might be difficult to model, like for example in the brain tissue. And again, since we are talking about translation, ease of manufacturing has been always a challenge. In conventional ones, and the process is mostly based on molding, curing over time, and then assembly, which is not easy for commercialization. So we propose in this area of organ-on-a-chip modeling with these challenges, we propose including a combination of using hydrogel systems and additive manufacturing, which is called 3D bioprinting, to have 3D bioprinted microfluidic chip devices that we can apply for the same application. We can mimic the different organs for drug screening and similar disease modeling. And in this process, what would be an ideal case? I mean, let make it some clear concept for the audience, for the people who are looking at this presentation. When we're talking about the micro tissue and when we're talking about the microfluidic part, we should look at the big picture. So a high throughput screening platform, when it goes to the market, when it goes to the clinic, it will look like something like this. You have maybe a site of storage place for waste and for the drug and media. You have some components that you are controlling the flow circulation, and you should have a set of parallel systems that are actually your base models for cell-laden parts, that you are considering the location that the cells are interacting with your agent, with your drugs, with your any therapeutics that you want to test. So when you're looking at this, you can see it's an engineering platform that the heart of the platform is the cell-laden part. The cell-laden part is the part that we can study the cell-drug interaction or cell-cell interactions in a specific tissue microenvironment. And again, since we are talking about translation, we're going to go to a commercialization process. We want to have ease of manufacturing. We want to always include cells in a patternable format, and we want to see how we can reduce the cost. There are some other considerations, but to me, as an engineer, these three are the main considerations that you want to consider when we are designing the experiment, when we are designing the system, when we are applying the system for those applications. So let's focus on, again, we focused on micro tissue. Now on the micro tissue, we see that we want to do the cell patterning. Now let's look at the current literature on 3D bioprinting, which most of the audience are very interested. And I know that the host of this series of talk also very interested in using additive manufacturing. Depending on the technology, this process can be based on inkjet deposition of a liquidish ink. The liquidish ink is very similar to traditional office printers that we had, and it's based on droplet deposition. So it's a contact-based method. Another method, which is based on the continuous paste of the material. Instead of having droplets, you have a continuous paste like a filament, which we call it as extrusion system. And in extrusion system, you have similar resolution to inkjet system. You have maybe a slightly lower speed, but it goes a much higher cell density, a much higher capacity for material selection. These two are contact-based systems, which materials and the system are always in contact. And the quality of the system, the quality of the construct, it's depending on that level of contact, the interface of the material and the substrate, the interface of the material and the additive manufacturing device. The other two techniques that I would classify as non-contact based system is based on laser induced forwarding of particles or droplets, which has some characteristics that might be interesting for some application, but is very limited to 2D structures. And also light-assisted bioprinting based on, for example, digital light processing, which has a good capacity for 3D. Compared to other systems, DLP or digital light processing systems are expensive to test, are expensive to develop. But in terms of the resolution, it has a high resolution, the same as the laser-induced system, much better than extrusion inkjet. And also, there is no limit on the material selection. The only limit for digital light processing or laser-based system might be the photosensitivity of the material. So it should be photosensitive material. And also normal, because it's not contact-based, it's a contactless method. You have a higher cell viability. And again, it might be a high cost at the beginning, but it goes to commercialization level. It goes the same level of cost as the extrusion and inkjet-based system. So now we reviewed and we had a concept of what are the existing methods. In terms of microtissue modeling, there are many published works in recent years. I'm summarizing some of the things between 2017 and 2019. So on some of the organs like liver, thrombosis for blood vessel issues that we wanted to test the drug, and also heart tissue, nervous system, kidney, and liver, that people use different bioprinters. And I try just to show the diversity. So any of those methods that I showed in the previous slide can be applied for a specific application because of the need, because of the simplicity, maybe because of the ease of use for that particular tissue. And extrusion used more commonly, and light assisted, for example, used for modeling liver as a two-material system, or inkjet was used also for liver as one of the pioneer works. So you can see people try to capture some feature size, to use different cell-laden bio-ink, which is the material as the ECM in the final product. So our solution here, again, we showed the existing system, we showed some examples. Our solution is based on digital light processing, DLP, that we want to use a DLP bioprinting for high resolution fabrication of hydrogel-based construct, for a rapid fabrication of complex structure in terms of geometry. And we want to see how we can modulate and we can improve or upgrade into multi-material fabrication. And again, as I mentioned earlier, it might be expensive for testing in the lab for a single platform, but for larger scale commercialization, it's very cost effective. And again, you can see in this slide, when you have a simple material, when you expose to light because of Fourier chains that are your cross-linking agent, they are attaching to the acrylation side or any photo responsive side in the material, and then they start to bond together. And by bonding together, they cross-link or solidify. When you have a solidified phase, it means that you're going from a liquidic phase or liquidish phase to a solid phase, that you have a 3D structure. And in our case, as I have experience in my postdoc training, we are using a very robust, economic, and highly modular material, a gelatin-based scaffold, which we use as metaacryloid, or we call it as GELMA because it's water cross-linkable. And we use also polyethylene glycol diacrylate as stability material or as the secondary material that helps the structure. And we use for our main purpose, we're going to have a highly tunable system that we can apply for different application, and gelatin would be a good candidate when you are dealing with cells, but when you don't have a cells in one region, PEGDA would be a better choice. Other hydrogel, when you have a need, for example, it can be hyaluronic acid, it can be fibronectin, you can always include in your system, because the bioink for DLP, it's very modular. You can always combine different components together. And now you select your material, which in our case, I mentioned here. Now we're going to see how we can control the microstructure, because one of the key concepts in screening platforms is the biotransport phenomena. And to control the biotransport phenomena, you have to control the microstructure. And the microstructure here can be controlled by material parameters like the concentration of the material, the type of the material, and also the fabrication factors like the timing of the light energy, and the cell property that also affects your microstructure. And we're going to study how they're going to affect. So we're going to show you the process of having the device, testing the device, and then controlling the microstructure as one example how we can come up with ideas for microtissue fabrication. This is a multi-material DLP system that was built when I was at Royal University in the Department of Mechanical Engineering. So we designed and fabricated the system over there. So it's based on an optical module that there is a mechanical stage on the top and a rotating optical table that helps for multi-material printing. So you can see the process when you have a 3D CAD file, you can slice it to images, and for a slicing, you can use open source softwares like a 3D slicer. And then you have your material prepared with cells. You include it in your petri dish or in your container. In our design, we use a UV grade petri dish as our platform, so it can be economic, it can be at low cost. And when you have the rotation, you can go from bioink 1 to bioink 2, or you can also go from bioink 1 to the washing liquid that you want to remove any residuals of the previous material. And then in the last step, you always have the printed construct, and then you can add your fitting and supports to have a full microfluidic device. So a real picture of the device is shown here in the left side of the slide. As you can see, you can have an idea of the physical size and how it looks like in reality. And again, you can always have a concept of having a multi-material, just as an example here, because this is something that you can imagine from a digital micromirror device that you can see in the device system. So when you develop the system, which I'm not showing all the details, one of the first things that we do is characterization. And the characterization starts with printability. In our case, we wanted to have a multi-material bioprinter, so we have to also check the printability for composites. The resolution was checked, you can see, using PEGDA polyethylene glycol at reasonably concentration between 40% and 60% PEGDA. You can see the resolution was close to 20 micron in 2D, and when it goes to the 3D shape, the resolution is at the range of 50 micron. So we always call the Z stage resolution or the high resolution as the practical resolution. And the truth is always better because you don't have any issue of the material, for example, viscosity or surface tension. For two material systems, we show some examples. We show the logo of the university to show the 3 material capacity. We were kind of limited to 3, but in general, it can be extended to more than 3. But I think for most of the needs that we had, 3 materials would be sufficient. So let's look at the process. I hope this video works. You can see this is a real-time video. It's not something that I think edited. So you can see the glass slide is attached to the sample holder. It goes to the UV grade petri dish to cure the first material. In our case, is the cell-laden gelatin. So the first material is the cell-laden gelatin, and then we wash in a buffer. And you can see after washed, it's kind of residual argon, and it goes to the second material, which is polyethylene glycol. That's the PEGDA, and it's for stability of the structure. So you have a cell-laden part enclosed with the PEGDA as the structure of the microfluidic chip, and you can see this is again real-time fabrication, so that you can see the timing is pretty quick, and per each layer, we only needed less than a second patterning. As you can see, the construct is ready to connect tubing, the metallic connectors, and to any kind of external source. And these are other examples that we made. And again, this is for creating a microfluidic hydrogel system. So continuing with this, the next step is showing the capacity of the machine for, again, our main purpose. You want to have micro tissue inside the microfluidic environment because you want to put in a high throughput screening at the last step. So the capacity of the machine was shown in and again, creating a structure out of PEG and gelatin, our choice of bioinks for different shades, different geometries. It can be a vasculature. If you are interested in modeling, for example, abnormal vasculature, then you can do the complex geometry. If you are interested in having, for example, two cell type models, you have that capacity that you can put on two sides of the channel and you can compare them inside the same environment. Or you want to have multi-material in the same block, you can always do that too. So now you do the characterization in terms of printability. You look at the structural property, how the structural property works. One of the key questions, how stable is the microfluidic hydrogen chip? And one of the easiest way is to do burst pressure. So we made the customized experimental apparatus to do the burst pressure. And we showed that the burst pressure is pretty high and it's very comparable to even PDMS system. And our platform was kind of very stable up to 1 week because PEGDA is not degradable and gelatin can be tuned in a way up to 1 week. You have very minimal variations in the sense of the property. Another aspect, when you're looking from the perspective of making a disease model, you are interested in the swelling ratio, how the swelling behaves in terms of having the fluiding environment. You can see the material was fairly stable for swelling ratio. And then biological response. When you have PEG, you always have viability at just the beginning. But over time, you want to work with a gelatin-based system that the gelatin helps you keeping the cell viability after 1 day, 2 days, 3 days that we try to show them. And now the next step after showing the biological response, we wanted to see how the hydrogel-based system can help us as engineers to control the biotransport of any transport-based phenomena. And again, the experiment was simple. We wanted to have two specific geometry that people may use for maybe mixing or other characteristics, and then see how the agent here is a fluid, is a food dye particle that's almost micron size. And we look at how the micron size particles diffuse from the channel into the hydrogel system over a period of 2 hours. And again, the system is polyethylene glycol based, and the diffusion rate again can be controlled by changing the concentration and other fabrication parameters. When you have that, you want to test further experimental apparatus, then you go for other geometries to see how you can create other multi-material models that you can again use for a screening application. And these are the typical geometries that people use, and we wanted to show the capacity of this. Now, we show the machine, we show how it works in terms of creating hydrogel-based microfluidic chips. Now, there are more questions to answer, how we can control the microstructure in terms of mass transport. One of the key aspects of biotransport is the mass transport phenomenon. And we want to see how we can control the mass transport property by creating agent gradient or drug gradient in our system. And we only pick one single fabrication parameter here, the UV exposure time, which is equal by UV energy. So only one parameter to control everything else. We keep everything consistent. We are changing the exposure time, and we use a standard drug model, the BSA particles, which is nano size, like between 100 and 200 nanometer size. And then we see the properties. So by changing the exposure time during the fabrication from 2 seconds to 4 seconds for a specific intensity, for a specific hydrogel concentration, you can see the particle diffuse or transport in a different rate when it goes from one to another. And we can make this as a device with different chambers that are in the same system with a single inlet, but different outputs, and each output is linked to that specific, for example, in this case, the diffusion rate or mass transport rate that you can control. And again, you can also include cells when you have the chamber inside the device filled by gelatin and metaacrylate and metaacryloid that you are encapsulating cells. You can also see the cell behavior. For example, doxorubicin as a drug model can be reached to tumor cells and see how the diffusion properties are changing the rate of drug exposure. And by changing the drug exposure, you have a different response after, for example, 12 hours of doing this process. Or another aspect that we can play around in our system is changing the cell density. You can change the cell density in each of the 3 chambers, and each chamber can be representing one specific case that can represent a healthy tissue, or it can be abnormal tissue or a diseased tissue. And again, this is not only limited to 3, it's scalable. When you're going to increase the number of chambers, you can use the circular design to add more chambers into your system, and you can add another circle at another layer, so you can increase the numbers going from 3 to 8, or from 8 to 8 of power 2, for example. You can always increase the numbers in a hyperbolic way. So you can see here, we wanted to show we can create gradients with 8 chambers. And also we could see the quality of our fabricated construct when you're looking at small channels, for example, if you want to use for mixing phenomena, or you want to use for even particle separation. So now we show that capacity, and then we show that we can change the cell density. When you are working with GELMA as the main bioink here, you want to encapsulate cells in GELMA, and you want to use in our bioprinting process. One of the questions is that how we can control maybe the mass transport properties even as a function of cell density. When you are playing with bioink, you can control the mass concentration from, in this case, we chose 5%, 7%, and 10%. But for those 3, we can also play with the degree of metaacrylation or the degree of photocross-linking from a very low to high. And also we can keep the exposure time as a fixed number, an optimized number that we can continue with the rest. And now we're going to see how the mass concentration and cell density are playing our mass transport properties, our biotransport properties. And we try to test this by a simple standard experiment in our lab to see if we can fabricate the particle-filled gel on one side, and the other side would be with no particle. We can see the mass transport in different cases. You're all aware of the 3 different concentrations, 5, 7, 10. They change the stiffness because higher concentration means a stiffer microtissue. But something that we're very interested to see what would be the diffusion property or the diffusion coefficient. You can see when you go from higher concentration to lower concentration, the diffusion actually goes high. So it's opposite to the modulus. So when modulus is directly linked to the mass concentration, diffusion coefficient is opposite. So for a lower mass concentration, you have a higher value. For a higher mass concentration, you have a lower. But that's another fabrication parameter that you can play around to change the biotransport characteristics. But when it goes to the case of cell-laden, when you are changing the cell density from case of control no cells to 10 million cells per ml, which is a very high number. So most of the literature works, they use something between 1 million to 5 million as the common numbers for most of cases that we use, but 10 million would be an upper extreme case. You can see that the diffusion coefficient is showing something very interesting. So the number is not going only down or is going only up. It goes to a low number for a cell density close to 0.5 millions, and then it goes up. So that gives us some idea that cell density also change the biotransport properties in our system. So even if you go use the bioprinter, make your design of the bioink, is not the end of the story. Even selection of the cell density affects your final output in terms of the mass transport property. And compared to elastic modulus, it gives you some idea that the porosity or elasticity are kind of interrelated. At some point, maybe the existence of the cell reduces the mass, the coefficient of the diffusion because they are filling the pores, but after a certain density, the presence of the cells maybe reduces the photocross-linking between the material bonding sites. So that might be a justification why we have that sharp increase. So we showed that how we can control the cell density and how we can control the mass transport properties based on the fabrication parameters and cell density. Another things that we were interested, and we said that for microtissue, you need additional component is making electrodes, making conductive electrodes out of the hydrogels, so we can include in our system how we can 3D print a microfluidic hydrogel-based device while there are some electrodes already built in the whole process. You are not going to do as an additional process. You're going to be built in, for example, case that you have in your chamber. And again, we started using the same backbone material, which is PEGDA in our case. And then we look at the literature. We found that P.PSS is a good combination. It's an organic semiconductor that people use with PEG. And when you mix it with PEG, it has a high quality for conductivity. And then we have been doing this. We have been optimizing the fabrication process and learning how we can control the conductivity property. This is an ongoing research, which I'm not going to show more details on this, but this is something that we are interested to add to our system. And as a characterization step, we showed that how the conductivity of P.PSS is comparable to, for example, graphene, standard material model that people use as a comparison. And again, the numbers are very comparable. It shows a high quality of conductivity that we can always use. So far, if you want to see what we have done and what's the step that we are taking at this time, we show that if you want to make a good kind of model that can be translatable to market, you have to do a kind of controllable, highly effective, cost-effective system. And in our case, we wanted to do microtissue modeling using light property, controlling the fabrication process by selecting of the bioink and also by selecting a fabrication parameter. For example, in our mechanical characterization, we can cover a huge range of stiffness, and each stiffness can be linked to one specific organ. When you are targeting a specific organ, you can pick the right bioink property, you can pick the right fabrication parameter, and then reach to that level of stiffness, for example. And other things, when you are dealing with screening platforms, you want to control the biotransport phenomena. You want to control the microstructure. And again, we showed that how we can use optical properties, how we can show the material composition, and how we can kind of customize the strategy by selecting the material and fabrication parameters together to reach a desirable level of diffusive property that you may need for your application. And again, we showed that the fidelity is still there when you are creating multi-material construct. You may have still high resolution and high control over this process. Future direction, I mentioned one of the things that we are doing is making electroconductive parts that we can use for sensing and actuation. But there are more steps to do. Conductive is one part, is testing different drugs. I mean, one of the things that you can show the capacity is actually comparing for FDA-approved drug models that people, I would say, they consider as a gold standard to check the quality of one model. And then how we can do this transition into the market, how we can scale up the process. That's another thing. When you want to go to the market, when you want to translate this technology, you need to do something that can be scalable. You want to do this in a high number. I mean, 5, 10 is not something that people would consider as a high throughput. You want to make it 100 or 500. So you can do 500 screening in the same platform. And that would I call as a high throughput application. So after these concluding remarks, I would like to thank the funding agency, the startup budget from NJIT and also Oron University, in addition to NIH and NJHF. My external collaborator, Dr. Nieto, who helped me with the optical setup, Dr. Wood, who is a cancer biologist at Rutgers, and Dr. Susan. And also the work was mainly the work of Anant Buzov, my first PhD student, that we built the device and we fabricated, construct, and tested. And another PhD student who works on using almost the same technology, but for tumorous fluid, which I didn't show any of those tumorous fluid modeling results here, that she also contributed to some of the results that I showed today. And I want to thank the rest of the team and the 2 undergraduates who helped a lot with this platform, Olga and Mike. And at the end, thank you again for inviting me to this talk. Thank you for your attention, and I would be happy to take any questions.
Thank you so much, Dr. Miri, for this great presentation. You can stop sharing and take a breath until I advertise our next speaker, and then we start with the questions. So our next speaker next Wednesday is Professor Marco Bonizzato from Polytechnic of Montreal, Department of Electrical Engineering, and affiliated to Department of Neuroscience at the University of Montreal. And he will be talking about neurotechnology to restore movement. And he also started his own company that he will talk about the story of his entrepreneurship journey also throughout his presentation. And also, again, we would like to thank Montreal Transmit Tech for sponsoring this e-seminar service. Okay, by that, I encourage the audience to put their question in the Ask a Question box while we are discussing some of our own questions. If you have any, please put it in the Ask a Question box down there. So one of our previous speaker, Ores, is asking, because you actually showed us some kind of cell-laden bio-ink and cell experiment, but he's wondering what kind of cells did you use in these platforms?
Sure. I try to be very focusing on the technology, not exposing other details of the work, and cell line is a key aspect. So in this specific case, and because I was at Oron University, that we were working with Cooper Hospital, and Cooper Hospital had a big center on soft tissue sarcoma. So these cells were fibrosarcoma. That's a fibroblast type cells, but the tumor cells. And now in NJIT, I have access to breast cancer cell line, which we are continuing now with breast cancer. So in general, the technology is for every tissue type, every cell line that you can select. But I would say tumor cells in terms of fibroblast size, if you will consider, because the size is a factor for some of the results that I showed. But in addition to size, there are not many other big factors you can replace with any other cells. But in this specific case, it was sarcoma.
Perfect. Thank you so much. And I have a question about the platform. So if I understood well, so the casing, the frame is PEGDA, and inside you have GELMA inside the channels, right? So, and I think you wanted to kind of replace the PDMS because of the drawbacks of the PDMS of drug absorption and this other stuff. But how about the permeability of oxygen permeability of the PEGDA? Have you studied that? I mean, because PDMS has this kind of advantage over other hydrogens or other materials?
Yeah, no, that's a very fair question when you go to hydrogen system, because everybody is comparing with PDMS. We try to start with more basic questions like how we can compare in terms of stability and stiffness and pore size and other things, but we have not studied the role of oxygen diffusion or oxygen property that might be different in hydrogen compared to PDMS. So far, again, when we go to tumors, you want to make a hypoxic conditions, and that's something that you want to consider in your model. As you can see in the platform, we don't have cells every place, right? The cells are localized in one specific location. As long as you make that location highly hypoxic condition, maybe you minimize or you control the nutrition delivery in a way that you make them more invasive, which we showed in another work, which I didn't show in this presentation, which we tried to make tumor sporoid in vitro and then encapsulate in gel and then fabricate with the rest of the same process. And then we showed that when you work with tumor sporoid, you already create that hypoxic condition because we did the gene expression and hypoxia factors. But again, that's a fair question. But in our case, since we are putting cells in a small environment, which we only need that part for most of the drug screening, we don't need a huge cell-laden part because that increases your cost. You want to minimize the cost by the limited number of cells that you want to use. Because I didn't show, but outside that big platform, you should have another room in a company that is your bioreactor that you are culturing cells in a high density, so you can use those to put in the system as a next step. If you want to minimize that, you want to minimize the tissue side, and then the rest would be your other, I would call material encasement. And PDMS requires lots of handling, and human labor is huge. If you think of translation into the market, if you think of labor cost, I think PDMS won't be that cost effective in the long run if you want to do high throughput, right? If you want to make 100, 500, making out of PDMS, it would be challenging. But when you go with additive manufacturing systems like optical system, it has the potential, right? It has the potential. But again, we didn't study the oxygen. That's a good thing.
No, that makes sense. No, that makes sense. I mean, for the logical next step, because sometimes you have normal condition, not hypoxia, and you want to have this oxygen transfer through your casing. Maybe one solution is that you have the open top kind of channel. So then the cells and the cell-laden hydrogel can get the oxygen from the top. But anyway, this could be kind of
and I can say something else for the audience that might be also interested. So, for example, Formlab now is selling a kind of it's called dental ink, but it's a biocompatible ink that they are selling. So we tried to use that ink as also an external layer on our structure. So when you do the multi-material, after you do it with PEGDA, can we add an additional layer? I mean, it's very hard when you're looking at the process because it's a layer-wise, and you want to keep PEGDA and that material in the same layer, and it's a huge chance of contamination. But we have been thinking of how we include that Formlab ink as an additional layer outside the chip, so we can use it as, again, you may also, that's almost no oxygen permeability, so you can always solve that issue that you just mentioned.
Thank you so much. So, Mohsen, do you have some question, maybe?
Well, I always have many questions, but I mean, I don't know how much time Dr. Miri has today. What is your availability, Dr. Miri? Can I ask like 2-3 questions from you?
Yeah, if you can finish this meeting before 1:10, that would be perfect for me.
Okay. So I'll just ask my first question, and then we'll see how it goes. So you're using hydrogels to make these microfluidic platforms, which is very interesting, and it has many advantages. One question that I have is your thoughts on evaporation, because these chambers, PDMS, we don't have that issue typically, but with a microfluidic device made out of hydrogel, which has water in it. What are your comments on the issue of evaporation and how this can be resolved if that's an issue?
No, that's a great comment. I mean, that's something that every student will deal in the first week of working with hydrogels in the lab. And we used to show just the successful pictures of anything that we do, but always when we fabricate, we put in an encasement that has a buffer solution as humidity. So we always, for example, if we put the hydrogen in a system that can have petri dish as the container, we always fill the petri dish with the buffer solution. And sometimes even we replace that to make sure that we always have clean buffer to keep it hydrated. If you keep it with no buffer, even for 10 minutes, you have a huge issue with dehydration. Because the structure is very small, so the surface is huge, the volume is small, so the dehydration is a big issue with hydrogens. And that's something that the only way is keep it hydrated with a bath. So you always have additional bath. But it's not difficult, and it's not challenging, because having that bath even in a commercialized setting, if you want to have high throughput, even it's something doable. It's something not very costly.
Okay, that's fair. So again, I mean, my next question is around the permeability of hydrogel to small molecules specifically. And when you want to do drug studies, and then you have this multi-chamber hydrogel microfluidic devices, then there is a chance of diffusion from one chamber to another chamber, and then cross product between these two chambers may affect the results. What are your comments on that challenge?
Yes, so far we were on this assumption that in our time frame that we are applying for example, the drug is like 24 hours, 48 hours. We don't have any issue of cross-contamination between the two chambers. That's a fair assumption for us. But if you want to make a long-term study, it might be something like a desirable output that you are interested. For example, you want to make, I don't know, a solid tumor in one side and vasculature on one side and a normal tissue on another side. And you want to create those as three platforms that you want them to cross-talk after 1 week or after 2 weeks, that the tumor part grow and the vasculature becomes very mature in terms of tight junctions. This is something that I would call as a desired output for some applications. That it's something that we have an ongoing project. We want to use that. But for the one that I showed in this presentation, it's a short term. So for short term, we assume that it hasn't been in place. But you're right. After a long, maybe 5 days, 7 days, cells migrate because they do this ECM remodeling. They digest the hydrogel and they move to other side, and also the liquid exchange might also lead to some crosstalk between the cells on both sides. So it can be an issue on one side if you do a long term, but it can be a desirable output that you can reach in a hydrogel setting, which you cannot reach in a PDMS setting, because in PDMS it's preset. The channel is preset, is not evolving, but in a hydrogel setting you have an evolving environment.
Very interesting, very cool. So one of the other advantages of your system is that that you can see, as you mentioned, you can see cell migration, and also I think because these gels, these are gels that you're using to make these fluidic systems. You can also look at them. You can take them out and then treat them as a tissue and then section them. Have you done this to look at the the section of these tissue-like systems?
Yes, yeah. That's an excellent point. Again, for general bioengineering audience, I think this is something that people always are interested. So immunostaining is one of the ways that we characterize the cells. And for what I showed here, I focus only on the technology, so I minimize all other parts. That one of them is how the cell behave actually. But we did this, but for cell-laden in a single distribution is not a big source of information, but when you are working with cell aggregates as a tumor spheroid, for example, that's something is very interesting, and also we have done it successfully. That's very challenging because cutting gels into sizes that you can put in a confocal microscope is challenging, but we have done immunostaining to see the cell behavior when they are culturing in a dynamic environment for like 7 days and even 14 days, because that's a very interesting result. But your comment is 100% valid and is mostly the final results of many existing disease modeling chambers, including ours and many other works that I'm sure you had other speakers in the past weeks that they showed. When you look at those results, is mainly they dissect, they stain, immunostaining or regular staining, and then they observe by a linear microscope or a confocal microscope.
Wonderful. And then another thing that came to my mind is whether you can digest the entire microfluidic device and collect cells. I know PEG is not easy to degrade, but are there other materials that you can use instead of PEG, and then maybe that they're not cell friendly, and then you can remove it, maybe hyaluronic acid, something that you can enzymatically or by other methods degrade them, and then harvest the cells. That's one of the challenges in macro organs and the chip, to harvest cells and then use them for maybe single cell analysis and things like that.
That's something that we had difficulty in the past 6 months or 8 months. Like we have been doing the same things. We wanted to do PCR on these isolated cells, and isolating cell-laden gel from the rest is a challenge. Isolating cells from the gel itself is another challenge, and purifying that final solution is something that we had also challenged. But those challenges are more like processing. It's not like a material challenge, and this is something that processing might be different for every material. Like, so for every individual that you use, so for PEG would be one specific material that you can use to separate it from gelatin, for example. Or when you are isolating cells from gelatin, you are using collagenase, but for another material it might be a different enzyme. But we try to optimize that. I wouldn't say it's 100% clean, but you get something usable for example, PCR measurements. But that's a fair disadvantage of hydrogel-based systems. So compared to PBMS system, one of the cons that we have is cell harvesting is an issue. I agree. Cell harvesting is so oxygen is an issue. Cell harvesting is an issue. Stability in long term is another issue when you compare with PBMS system.
But definitely this can be solved. Sorry, Human. I think it's
one last question, because Dr. Miri is leaving and I want to ask him, so maybe I cannot find him. So is that about the transparency of the casing? Because PEGDA, as I see, is orange. So can you see it under the microscope, the cells, the hydrogel? Because PDMS is transparent, right?
No, orange color is coming from the photoabsorber that we use. The photoabsorber is in orange colors, and when I was doing a postdoc, we didn't disclose the information of the photoabsorber at that time because it was new to everybody and nobody would find a good photoabsorber. These days are common, but that's a commercially available biocompatible photoabsorber. When you include cells will be alive with maybe 85% cell viability. They may diffuse into the cells when you use at a high density, but in the normal density that we use for this work, we showed that we had also preliminary results of PEGDA without absorber, PEGDA with absorber at different concentration and different concentration of cells, and we found the threshold of toxicity. So for our preliminary, we had that threshold, so we always used something below the threshold. But the orange color is coming from that absorption for 385 nanometer wavelength that we use. And again, that's a key message. 365 is toxic to cells. 375 is the threshold of becoming non-toxic energy for cells. So 385 is fully biocompatible. Even if you increase the timing, if you increase the energy, it barely damages the cells. And with this photoabsorber for that range, maybe if you change the wavelength of the system, you need another photoabsorber, because this photoabsorber works for this range. You will see this orange color.
Thank you so much. Since you don't have more time, I would like to thank you so much for accepting our invitation and for your great presentation. And I would also thank Mohsen to ask good questions. And also the audience who listen to us and always they follow us. For getting the updated information for the next talk, just go to our Twitter Twitter account, Translational Biomedical Engineering Seminar Series, and also to see the recorded presentations from the past 2 years. We have YouTube channels that you can go and subscribe to get the updated recording as well. Thank you so much, and see you next Wednesday for Professor Bonazito talk on neurotechnology for restoring movement. Thank you so much, everyone.
Thank you very much.
Yeah, have a great day. I'm going to close.
Bye-bye.
Bye.